Hey students, welcome to another video. Today we will be covering short answer questions from chapter 2 periodic motion. And first question we have is, if the length of a second pendulum is increased by 200%, will it lose or gain time? So our answer should be like, as we know that the period of the simple pendulum is given by the formula T equals to 2 pi root over L by G, where T is period, L is length of pendulum, and G is acceleration due to gravity, right? So if the length L is increased by 200%, it means that new length becomes 3 times the original length. That is, T new will be equals to 2 pi root over L by G. Putting the value of L, we get T new as root over 3T. The period T increases by the factor root 3, that is approximately 1.732. This means the pendulum will take longer time to complete each swing, and by increasing the length of second pendulum by 200%, the period increases, causing the pendulum to gain time. Next question we have is, what do you understand by a second pendulum? If it is taken to the moon, will it gain or lose time, and why? It has been asked 2 times, so it is important question, we must say. So answer should be like, a second pendulum is a simple pendulum with a time period of 2 seconds. That is 1 second for a swing in one direction and 1 second for the return. And the period of a simple pendulum is given by the formula T equals to 2 pi root over L by G. On Earth, the length of second pendulum is approximately 0.994, which we can say about 1 meter. And since the Earth gravity is 9.8 meter per second square and the period of pendulum depends on gravity, we substitute G moon into the formula as T moon equals to 2 pi root over L by G moon. And on the moon, gravity is weaker, which is about 1/6 of the Earth gravity. Since gravity in the moon is smaller, time period in the moon increases. This means that the pendulum will take more time to complete one oscillation. And if a second pendulum is taken to the moon, it will lose time because the lower gravity increases its period, making it swing more slowly. Third question we have is, a simple harmonic motion is represented by y equals to a sine omega t plus phi. Find its acceleration. Our answer should be like, the equation of simple harmonic motion is given by y equals to a sine omega t plus phi. Here we have to find its acceleration. So first we have to find the velocity and then differentiate it, and we will find out the acceleration. So we know that velocity is the first derivative of the displacement with respect to time. So on differentiating given equation, we can find out velocity as a omega cos omega t plus phi. And we know that acceleration is the second derivative of displacement with respect to time. So a will equals to the differentiation of the velocity, that is equals to minus a omega squared sine omega t plus phi. And since we know that y equals to a sine omega t plus phi, we can rewrite the acceleration as a equals to minus omega square y. Hence the acceleration of particle in simple harmonic motion is a equals to minus omega square y. This shows that acceleration is directly proportional to the displacement and always acts in the opposite direction, confirming the restoring nature of SHM. Next question we have is, how is the frequency of vibration of a simple pendulum related to its length? Estimate the frequency of a second pendulum. The frequency of a simple pendulum is related to its length by the formula F equals to 1 by T. On putting the formula of time period, we get F equals to 1 by 2 by root over G by L. That means F is inversely proportional to root over 1 by L. The frequency is inversely proportional to the square root of its length. A second pendulum has a time period of 2 seconds meaning that t equals to 2 seconds. And using the frequency formula, we have f equals to 1 by t, right? So equals 1 by 2 equals 0.5 Hz. That means the frequency of a second pendulum is 0.5 Hz, meaning it completes one oscillation every 2 seconds, half an oscillation per second. Another question we have is a simple harmonic motion is represented by y equals to a cos omega t plus phi. Find its acceleration. So our answer should be like the equation of simple harmonic motion is given by y is equal to a cos omega t plus phi. And we know that velocity is the first derivative of displacement with respect to time. So on differentiating the given equation, we can find out or calculate the velocity as minus a omega sine omega t plus phi. And we also know that acceleration is the second derivative of displacement with respect to time. On differentiating the velocity, we will get acceleration as minus a omega square cos omega t plus phi. Since the given equation y equals to a cos omega t plus phi, we can rewrite the acceleration as a equals to minus omega square y. Hence, the acceleration of particle in SHM is a equals to minus omega square y. This shows that acceleration is always directly proportional to the displacement and always acts in the opposite direction, confirming the restoring nature of SHM. Another question we have is, a pendulum clock is taken to the moon. Will it gain or lose time, and why? The period of simple pendulum is given by the formula t equals to 2 pi root over L by g. Since Earth's gravity is equals to 9.8 meter per second square, and on the moon, gravity is weaker, which is about 1 by 6th of Earth's gravity. We know that the period t is inversely proportional to the square root of g. When the pendulum clock is taken to the moon, the weaker gravity increases the time period. We know t moon equals to 2 pi root over L by g moon. Since gravity on the moon is smaller, time period on the moon increases. This means the pendulum will take more time to complete one oscillation. Hence, a pendulum clock will lose time on the moon because the lower gravity increases the pendulum's period, making it swing slower than on Earth. Next question we have is, explain why soldiers are ordered to break steps while crossing a bridge. So for this question, our answer should be like, every structure including bridge has a natural frequency at which it vibrates, right? So if soldiers march in steps, it can create a periodic force which then match with the natural frequency of the bridge. It can cause resonance, leading to the large oscillations and potential structural damage. When soldiers walk out of step, their footsteps create random, uncoordinated forces instead of a single amplified rhythmic force. This prevents resonance and keeps the bridge stable. Thus, soldiers are ordered to break steps while crossing a bridge to prevent resonance, which can cause dangerous vibrations and lead to structural failure. Our next question we have is, why are bells made of metal and not of wood? Explain. So for this question, our answer should be like, bells are made of metal because metals produce louder, clearer, and longer lasting sounds due to its high elasticity, density, and resonance, while wood absorbs sound and dampens vibration. That's why bells are made of metal and not of wood. Next question we have is, a pendulum clock is in an elevator that descends at a constant velocity. Does it keep correct time? If the same clock is in an elevator in free fall, does it keep current time? When the elevator moves downward at a constant velocity, there is no change in acceleration, right? And the acceleration due to gravity remains same. So the time period of the pendulum remains unchanged. Since the period is unaffected, the clock gives correct time. And for the second half of the question, we have given in a free fall, the elevator accelerates downward with acceleration g, and inside the elevator, everything, including the pendulum, is in a state of weightlessness, that is, zero effective gravity. Thus, the effective gravitational acceleration becomes zero. If the gravitational acceleration is zero, then t becomes infinite, meaning the pendulum stops oscillating. And as a result, the clock stops working and does not keep time at all. Thus, in free fall, it does not keep correct time because the effective gravity is zero and the pendulum will not oscillate. Next question we have is, a body is moving in a circular path with constant speed. Is this motion simple harmonic and why? So our answer should be like no, because a body moving in a circular path with constant speed is not undergoing SHM because the acceleration is not proportional to its displacement, and the restoring force in SHM always acts towards a mean position, whereas in circular motion the force is directed toward the center of the circle. Next question we have is, what are the drawbacks of simple pendulum? So the drawbacks of simple pendulum are, the theoretical model assumes a massless and perfectly rigid string, but in reality the string has some mass flexibility which affects the motion, right? And the time period depends on gravity, which varies by location and altitude. And changes in temperature can cause the length of pendulum string to expand or contract, affecting the period. And in real conditions, air resistance gradually reduces the amplitude of oscillation, causing the pendulum to lose energy and slow down over time. Another drawback is, the simple pendulum assumes an ideal scenario where there are no external forces other than gravity, but in reality, factors like wind and vibration affect the motion. Another question we have is, on what factors does the period of a simple pendulum depend? The period of simple pendulum depends on the length of the pendulum. That is, the period is directly proportional to the square root of the length, the acceleration due to gravity. The period is inversely proportional to the square root of the acceleration due to gravity. Next question we have is, if the length of a simple pendulum is increased by 4 times its original length, will its time period change? If yes, by how much? Since the time period is proportional to the square root of the length, the time period of a simple pendulum will change if its length is increased. Let's say the initial length of the pendulum be L and its initial period be T. The period of a simple pendulum is given by the formula T equals to 2 pi root over L by G, right? So if the length is 4 times original length, the new time period T dash will be 2 pi root over 4L by G. On calculation, we get T dash equals to 2 times original time period T. Hence, if the length of pendulum is increased by 4 times, the time period will be double. So, the new time period will be twice the original time period. Last question we have is, if a pendulum clock is taken to a mountain top, does it gain or lose time? For this question, our answer should be like, since the period is inversely proportional to the square root of the acceleration due to gravity, and on the mountain top, the value of gravity G is weaker because gravity decreases with altitude. As the value of G decreases, the time period T increases, causing the pendulum to swing more slowly. Hence, a pendulum clock loses time if it is taken to a mountain top. So this much for today. If you haven't subscribed to our channel yet, please hit that subscribe button and turn on the notification bell so that you don't miss any updates. Till then, stay safe. Bye.